Hello, my name is Laura Castano, and this is Lab 4 of Physics 2211. In this lab, the main objective is to observe and measure the motion of a mass swinging in an arc while it oscillates in a spring. Then, with these observations, we will create a model that follows the motion and that measures in its energy changes. Some key ideas are first, Newton's second law of motion to predict the motion of the mass because we know the net force at every single point. This net force is made up of the spring force and a gravitational force, and here we can see its equations. The other main principle is the energy principle, and as we can see, it defines a system of the spring, mass, and earth. And because there's nothing in the surroundings, so there will be no work or energy change. The change of the energy will be equal to the change of kinetic energy plus the potential spring energy and the potential gravitational energy. Okay, so now in Tracker, here we can see how I track the X and Y position for each frame in the motion of the spring. I chose my my Y-axis so that the positive y-axis is upward and the negative y-axis is downward. Okay, so with the data of Tracker, I could calculate the gravitational force by doing the dot product of the mass and the gravitational constant, which is negative 9.8, which will get a resulting value of negative 3.94 newtons. Because the net force also consists of the force of the spring, then I had to calculate first the spring constant K. In order to do that, I used the formula of the oscillation time, which is this one. And then with that formula, I isolated the K, so the spring constant, in order to find it. So I plugged in the values, which gave me a 6.67 newtons per meter. After that, I calculated the relaxed length of the string. So in equilibrium, the y forces cancel out, so I could set the force of gravity equal to the force of the spring. And then I isolated L naught, and because I had the value of L and the rest of the values, the gravitational force we just found, we could find the relaxed length, which is 0.109 meters. Okay, so now that we have all this information, we can update our code. The first step is to further update the system mass, which is 0.402. And then we had to update the initial conditions, which we got from Tracker, and the ball's initial position vector is this one. Then we had to plug in the constant of gravity, which is 9.8, and the spring constant as well as the relaxed length, which we just calculated in the previous step. Then we had to calculate L, which is basically the ball's position minus the spring position, the L hat, which is the L divided by its magnitude. So in order to find the S, is basically the magnitude of L minus the relaxed length. Then we had to compute the system's energies, and basically we added the energies, the kinetic energy, the gravitational potential energy, the spring potential energy that we just showed that I showed earlier, and then we calculate the total energy by adding all these energies. The next step is to update the while loop with the final time that we calculated in Tracker, which is 9.972 seconds. Also, we had to calculate the gravitational force in the same way that I showed earlier, as well as the F spring. And because F net is composed by F spring and F grab, I also updated it here. The next step is using Newton's second law or the momentum principle to first update the velocity as well as the object's position. And with that new position, we could also update the L. Also, we had to calculate the energy changes using the new position and velocities, and we added it just here. But at the end, I also added the change in energy, which is basically the final energy minus the initial energy. Okay, so these are the results of our code, and this is how the spring moves in this trajectory. The first graph, which is the change in energy versus time, depicts the gravitational potential energy and the spring potential energy switching back and forth. However, the kinetic energy oscillates as the mass speeds up and slows down. Nonetheless, we can notice that potential energies oscillate opposite to each other, while the kinetic energy is oscillating more uniformly. But we can notice that the change in energy is almost all flat, which shows that there was no change in total energy or the total motion of the mass. The second graph is the prediction versus observed motion. We can see that there was a noticeable discrepancy, and this may be because we didn't take into consideration the drag force. So in the future, if we could take into consideration the drag force, maybe our predictions would be more accurate. So for my model, is the energy principle satisfied? And the answer is yes, because the energy principle basically implies that the energy of the system is equal to the energy of surroundings. And because there's no surroundings, there's no work. Hence, the surroundings have no interaction with the system, so the change energy should be zero, as it is demonstrated by the orange line in the graph. So if we compare the time period of the oscillations of the x and y components, the x component is 1.58 seconds and the y component is 1.82 seconds, and the difference between both will create a discrepancy, an even bigger discrepancy with the k constant, which will affect the force of the spring, hence would affect the net force. And the y component needs to be used as it is in the axis of the spring.